All right, so this is going to be a demo on how you can get started on your data path. We'll do quite a few pieces in this video, and then you'll just finish it up on your own. So the first thing we want to do is on Canvas, go to your files right here. And in our files, you'll see that there is a TSC library control file right here. You want to download that so we can import it into Logisim. So the next thing you'll want to do after you download that file is put it in the same folder as your project file is. So your project file is the one with your ALU and your ALU bit and your adder and your mux. So once those are in the same folder, you're ready to import this into your project. Now, this is a diagram of what our goal is in this project is to make our data path. So the data path, we'll hopefully have lectures before this describing this in more detail. But the data path is how information or data moves around through our ALU and gets its way into different registers that we have right here. This is our goal. So I'll go ahead and open up my data path or my project. And you can see here, hopefully you can open your project to follow along. You should have your ALU and your ALU bit. And what we can do is go up to the project menu, and then down you'll see a load library, and go ahead and click on Logisim library. Now you'll see the TSC library control file that you downloaded. Go ahead and click on that and click open. Now we have that library inside of your circuits that you can use. Now, one important thing is Logisim has actually not imported all of those circuits into it. It's going to rely on that file. So you can't delete that file and you can't move it. Keep the TSC library control file in the same spot. Also, don't rename it. So I'm going to go ahead and add a circuit. I'm going to call it the data path. And this will actually be the main circuit of your computer when you're running your programs. This will be the circuit that you're looking at. The next thing we want to do is we want to grab our ALU down out here. Now I recommend zooming way down. Put your ALU down here somewhere. Just give yourself plenty of room to put all of the different components that we're going to have to put on here. Then you can zoom back in and scroll over and down until you find it. And now we can drag our bus 3 wire down and pull it all the way over here. All right, so off camera, I finished dragging that bus 3 wire up on both sides, and then I have my bus 2 wire that I drug up and my bus 1 wire. So you can see I am trying to do this right here, and then I have my bus 1 and my bus 2. I'm going to go into my wiring and I'm going to grab those probes. It will be ever so helpful right here. I'm going to put a probe on the top of each one of these wires all the way across. So now you can see on my probe, 2 probes on bus 3 on either side, 1 probe on bus 1, 1 probe on bus 2. Now you can always go into here and change these. It's probably be best to use hexadecimal to see that. So now we have at least probes so we can see what's on this. So the next thing that we're going to do is we're going to build this part right here. We're going to put down our PC counter. We're going to have a switch bank so some people can put in a number and load our program counter, point our program counter wherever they want. And we're also going to make sure our PC counter connects to bus 1. And hopefully you know these arrows mean that we're going to have a tri-state buffer there. So I went ahead and did this off camera, but just to see what I did, I went and I grabbed the register right here, placed it down. Notice the D is the input, the Q is the output. Okay, so we place that register down. We hook the clear to our master reset button right here. And hopefully in the other lecture, this is low asserted. So when it's off, it's on, and when it's on, it's off. So it's just switched, and that's what the little circle up here means, is it's low asserted. So we hook that up to our reset, And we take our clock right here. I just did a little circuit right here, and this helps us. Sometimes we want bus 3 to get into our register, and other times we want the person to be able to click the wires like F, F, F5, like we've done in previous labs like that. And then we got a little push button. So again, this is just an input switch right here, one of these that I turned into 16. And then this right here, you'll find in, I believe, the input, output. It's just a little button right there that we dragged out and put a button right there. This again is a input switch of length 1. This guy right here is our tri-state buffer. So we'll place him down. We placed him down. We hooked PC to bus 1. So hopefully when you learn about the data path, you learn about all of that. And so whenever we put a number there, I could show you, I can hold down this button. Grab that. And this has to be a high voltage for it to work. Or we can press down our button. And there we go. We got FFF5 onto our into our register. So now we got a little load PC button. This guy right here is just a mux. So I grabbed him out of the plexers right here, just a multiplexer. Let me show you the settings that I put on this multiplexer. There's 1 select bit, 16 data bits. So that's like 16 wires. And it just chooses, do we want this to connect to here or do we want this to connect to here? So if it's a low voltage, we get this. If it's a high voltage, we get that. And this little push button in that little circuit that I did right here allows us to do that. So that'll give us our program counter. I also put switches on all of my operations right here on my ALU. So you want to put switches there so that you could tell your ALU what operation to do. Now we're going to work on this piece right here, which is the biggest and most complicated piece of the project. So we could see here we're going to have a tri-state buffer, a register, the memory address register, another register called the memory buffer register. And if you notice, whenever there's 2 arrows pointing into something, that means we got to have a mux right here, except for this where we have tri-state buffer. So there's going to be a mux right here and our memory. So we're going to build that. So I went ahead and did some work off camera for this. Here is my MAR right here. So again, just another register. You get that out of the library that you imported. Connect the reset to the master reset switch. So you can see I got a tunnel that's my master reset. And then we got a switch bus 3 to MAR right here. Then so you can place that down. Then the next piece you might want to place down is memory. So where do we get memory from? Well, there's a memory folder over here you should have. And just grab RAM, RAM is what you want to grab out of here. Place it down like that, and then you'll have to change the settings.
And so starting from our default RAM right here, we'll need to change for here the address bit width to be 16, our data bit width to be 16, our enables to be use line enables, and then lastly, appearance, change it to classic Logisim. Just helps it look a lot cleaner.
So my address lines come in here. And then the data, if whenever we want to write to it, if we want to write new stuff into memory, we put that right here. And the memory out right here, this is the information coming out of the memory. So if you notice, we have 0 right here, all zeros right here. And here's our memory. If I click and I edit the contents, this is memory location 0. I'm just going to put the word dead in memory. So this is a cheap trick where we can just type in what we want to be in memory. And so we see that the address 0, so this is the address, we can see that the dead comes out. Now the dead will come over here into our mux right here. Let me show you the principles of this mux. Again, one select bit, 16 data bits, so we can do that. And now we can see that the data coming out of memory will get put into this mux, and now it's feeding in to the input of our memory buffer register. When we go from a low to a high voltage, then the word dead gets put there. And then we have another tri-state buffer that connects us to bus 1. By the way, this up here, I don't know if I showed you, but that connects down to bus 1 right here from our ALU. And if you can see right here, I also put an input. I just grab a switch bank, a tri-state buffer, and input to bus 1 there. So one thing, because all these are low asserted, when you first open your file, these will all be off, which really means on. So you have to go and turn them all on to shut them off. So anyway, again, this is just another register, another probe, NOT gate, and that should be your memory. And just in case you were wondering, this right here, of course, is bus 3 that kind of comes all the way down out of my ALU right there. So next, let's work on this piece right here. We'll work on one of our registers right here. And if you notice, a bus 3 comes into the input of the register, and then the register splits and connects 2 times, once to bus 2 and once to bus 1. Now you can see here, bus 3 comes out this way, comes up to here. And if you notice, in order for to have the D be the input, like we had in our registers over here, so you know it's the D is the input on all of our registers, I turn this register upside down. So reset's now on the bottom, the clock is now on the top, the D is now on the right side, the Q is now on the left side. So, and then coming out, we can see that this splits 2 ways. So one will hook up to bus 2, and the other one hook up to bus 1 right here. So we could see that those hook up that way. And so that's how all of our registers work. And again, with this probe, so we can see the value inside of the register right there. Now I did this for register 0. You're going to have to do it again for register 1, 2, and 3. So you're going to need 4 of these diagrams total. The only difference will be that this will be bus 3 to register 1 to bus 2, register 1 to bus 1. So we have all of that there. As you can see, I have put my 1. This is a hard-coded 1. This is just to put a 1 onto our bus 2. That's to increment our program counter. And so how did I do that? Well, I went and I grabbed the constant and I made the 16 data bits wide and turned it upside down. And now you can connect that. This here is just a tri-state buffer. And this again, I enable switch, and then I just took this guy right there. And if you notice, that's all zeros, so we can just say 0, 0, 0, 1. So that's just the number 1 that we can hook in to there. So I should probably pause and finish up all your registers right now. We've made this part, we made this part. I got an input device on there. The output device, you could just put a probe on bus 3 somewhere. Or you can have it be a register. You could get more fancy if you want, but a probe would do. And then hopefully I did 1 of these. You want to do the other 3 of those, and we've done that. So our last thing is the instruction register. So instruction register is going to look a lot like these, except for they're going to have 4, it's going to split 4 ways and connect to the bus in 4 different ways. So here's my instruction register, and you can see I have the 4 tri-state buffers. Now 2 of them will hook on to bus 2, and the other 2 hook onto bus 1. So we got, again, the upside down register. We got bus 3 to IR, and now we have the 4 connections. So I'm going to show you how you might do one connection of the 4, and then you'll have to do the remaining 3 on your own. So the one I'm going to do is upper immediate to bus 1. So if you read through this, your assignment, that says this is for the load high immediate instruction, or the LHI. So what we do is you go to your home page, click on readings, and then click on instructions. And then we'll go find the load high immediate instruction. And now you have to read this and hopefully make sense of it. But the basic idea is this is information telling us what register and what the instruction is. That's not really a number that we want to become part of our data. Remember, this is the data path. We're not trying to put our instructions into the data. But this immediate value is a number that we want to become part of our data. So we want to take these bits 0 through 7, out of the instruction and place it onto one of the buses so it could become part of our data. So if you look here, the 8-bit immediate value is concatenated to 8 bits of 0, the immediate value being the most significant half of the word or half word, and then the results is placed in RT. So, and then this is a little thing, the double hashtag means concatenate. So we have bits 0 through 7 with at the top bits and 8 zeros down here. So we want this to get shifted up into the top bits from bit 15 to 8, and then we want to fill this in with 0. So we want to take the instruction coming out, we want to take this immediate out, and then we want to put it on the bus, but on the upper bits. So how I'm going to do that, I'm going to grab a splitter right here. This is after I've kind of split this up to go 4 different ways. And we'll connect one of these things to the splitter. It's not liking that because our splitter needs to be a 16 bits wide. And I'm only going to fan it out 2. And just by that, and I'll zoom in here so you can see it a little bit better. You can see this wire has bits 0 through 7. So that is the immediate value. Now we want to hook that up to this guy, but on bits 8 through 15. So I'm going to grab another splitter. And in fact, it might be easier to just copy and paste this one. So you can see if you have more room to work with, this will be a little bit easier. That's why I recommended you zoom way out and give yourself plenty of room to work with. Okay, so now I'm going to feed the immediate value into the upper 8 bits of this instruction right here. And I'm going to call this upper immediate to bus 1. And we'll put that on the south right here. And now, now this is okay. This is information coming out of here. These wires will just die. But this does need some information, so we know that we want to concatenate 8 zeros there. So we can just grab a constant, make it 8 bits wide, and turn it upside down and connect it there. So, and now we've done what the instructions say. We took the immediate value that was in bits 0 through 7, we placed it in the upper bits 8 through 15, and we had the lower bits be filled in with zeros. Okay, so you'll want to look at the target address. You're going to look at a jump instruction right here. For the signed immediate, you'll probably look at the add immediate instruction. Now remember, you don't have to do the adding, we just have to get the immediate onto the bus. Your ALU will do the adding. And then right here, there's the unsigned immediate instruction, and you can look in the reading, there's an instruction for that, probably the OR immediate or RI instruction that tells you how you take the immediate value out of the instruction and place it onto this, and we got to fill it up with zeros or something else. So make sure you read that guide to know what you fill it up with. So just finish up that. Of course, you need to finish up all of the other registers. I only did one register here, but other than that, you should finish it all up. All right, now I'm going to show you how to pass off. So we're going to simulate the fetch sequence, and then we'll test a few other things to make sure everything is working. So hopefully you learned about the fetch sequence in another video or in our class period. So what we're going to do first, and I've already done it, but I'll show you how, is we'll edit the contents of memory. And in the third spot, so this is the 0, 1, 2, 3. So in the third spot, we're going to put the word dead, D-E-A-D. This is something really easy that we can recognize. So remember, this is a hex number, so these are really the hex numbers right there. So once we got dead in the third spot, we'll go up to our program counter right here. Now, make sure that you got all of these tri-state buffers shut off. And remember, a high voltage means off. So make sure you got all the tri-state buffers shut off. But check all of these tri-state buffers, make sure they're all shut off. So they all are. The other thing is make sure all the operations are shut off too to start. Okay? And then make sure this is a high voltage or else your push button won't work. So we'll put the number 3, the memory address 3, and we'll click this as like our load PC button. And you see we got 3 into our program counter. Since we got 3 into our program counter, we go down here, we turn on TRA1 right here, and let's see. Oh, and then turn on PC to bus 1 too, so we could get the 3 onto our bus 1. And then TRA1 passes that 3 through there, and we're going to clock it into our memory address register right here. So bam, now it has 3. So remember, the registers change their value when it goes from a 0 to a high voltage right here. So now we got the number 3 right there. Okay, now memory should be looking up what's that memory location 3. It's already did it. It's pretty fast, but as our computer, it'll take a little time to look that up, and we're going to take advantage of that time to add 1 to our program counter. So we'll turn on 1 to bus 2, turn off TRA1, and turn on add in our ALU. So now we should be having 3 from our PC counter on bus 1 and 1 on bus 2 from this guy right here. And we'll see that they're adding up to 4. So now that we got the 4 up here, we can go ahead, and this is how the computer controls it. This is our push button, a user, but the computer controls these switches. So this switch will toggle, and we should see 4 right there. And if you want to try it a little more, every time you toggle it, it'll keep adding 1 to it. But just do it at least once as you test it. So again, you'll need to make a video of this, of you doing this, to pass off your assignment. So now that we got that working, we can shut him off, shut off that, and shut off that right there. And now we'll go ahead and go to memory right here. So memory is now looking up, and we got dead coming out here. So make sure our mux, instead of selecting bus 3, should be selecting the dead coming out of memory. And we'll go ahead and clock that into this register here. So you see now this register has the word dead. We'll put that onto bus 1. So now dead coming out onto bus 1. That's our instruction, our pretend instruction. We'll turn on TRA1, so we got dead out onto bus 3. And go ahead and clock that into your registers here. Do it for all 4 to make sure that all 4 registers work. And then last but not least, your instruction register. So now we have dead coming out of our instruction register right there. And then we can shut this guy off right there. And now the last test is to make sure you hooked all these things up right. I'll show you the right answer for this upper immediate right here. when we turn it on, if you notice the AD, the lower bits, got shifted up to the upper bit. So we got AD 0, 0. So zeros got put in for the lower bit. So that's the right answer for the upper immediate. I'll tell you the right answer for the unsigned immediate. If we were to do this, if it's unsigned, then it should be 0, 0 AD right there. The signed immediate should be FF AD. So that's the signed immediate. And then last you have the target. So when you turn on the target, it should be 0 EAD. That's what you should get. Unless you go over to your program counter right here and put in something in the upper 4 bits. So this might kind of give away the answer and what you need to do for the target right here. But when you do that, then you should see C. Notice I got C in my upper 4 bits of my program counter. So we should see whatever's there up here. And then EAD down here. So the EAD should be in these 4 spots. And then the upper 4 of the PC should be in that spot. So to pass off, make a video starting with editing your memory. Just make sure we see dead in there. Then go through the fetch sequence, clock dead into all your registers as well, and then show me turning on all of these switches. And that's the video you'll make to pass off your assignment.